John is a professor of mechanical and industrial engineering here at UW-Platteville, and Joseph is a professor of chemistry also here at UW-Platteville. Please welcome John and Joseph.
Okay. Thank you. The topic of our presentation is mechanical properties of polyamide matrix dairy protein composites that were fabricated using selective laser sintering. The purpose of the research is to transform dairy wastes, particularly casein and whey, into engineering components using some sets of additive manufacturing processes. And the process we are presenting on today is called selective laser sintering. It converts powdered materials into solid objects. This is the agenda, the motivation, the materials we used, and the processes. The print qualities will be assessed in terms of a lot of data that have been generated, and we will evaluate the mechanical properties and compare. Well, the motivation arises from the fact that we hear about waste in the dairy business. We hear of waste in the cost of processing dairy products, and we also know about casein. And those materials historically have been proven to have some polymeric properties, and they have also been used for some items in the past. And we also know that there are pressures in terms of competition with dairy milk in the market. There are a lot of crop-based milk products that are becoming very popular, and increasingly they'll be popular, and they'll be cutting into the market of dairy mix with time going forward. And we also want to promote circular economy in terms of looking into biological materials that can be used for engineering applications, which are becoming popular now, and with increasing demand based on the realities of climate change. So we all know that well, I wouldn't say we all know, but it is common knowledge that milk contains several components, one of which is protein. And the protein is about 3.3 or thereabout in percentages. And we also, as I've mentioned previously, identified uses for casein and whey. We are doing a kind of a parallel study at this time. The button shown there was made by casein in the past, and we are curious to see what can we do with casein using the processes that we are working on currently. So previously it had been used for additives, for adhesives, for buttons, for paints, and some other polymeric materials. So to start with, we are not converting casein directly to final product, but we are taking it step by step. We have proven materials that are used for fabricating engineering products in the market that are commercially available. So what we do at the initial time is to blend casein and whey with those materials to evaluate how much the properties change. So the preliminary data we have that is being presented here are based on those combination of materials. So we have the PA12. PA12 is polyamide 12. We're also working on polyamide 11 that are commercially available and being used in the market with proven strength properties. Then we have on the other side, casein broken down into fine particles. Although with the preliminary work presented here, we couldn't get to as fine particles as much as we wanted, but just recently we were able to find ways to get it very fine, very close to what we want it to be to improve the properties that we are aiming at. Then for engineering analysis or for engineering applications, if you want to use a material for fabrication, we have standard ways for evaluating the mechanical properties, which include tension testing, include flexural testing, and also impact analysis. Well, for tension testing, I have a cane here just to illustrate. If you want to test how much you pull a material until it breaks, what stress level is able to break it. Then if you talk about flexure, imagine having a beam like this and you apply load. How much of load or how much of stress do you apply to bend it and to eventually break it? And also for impact, how much of sudden impact do you apply on the material before it breaks? So those are standard mechanical engineering tests that we designed and subjected our samples to. So for tension testing, we have clearly improved strengths for our fabricated samples that are based on composites of casein addition to the commercially available material. And all the percentages of compositions of the materials demonstrated significant improved strength. And in the course of evaluation, we discovered that our material was becoming more brittle with the addition of casein. So we thought of other things that we could add that could reduce the brittleness. So that was when we got some improved data in the process and significantly higher strength and ductility of the materials were improved. Then we also have stiffness. Stiffness is resistance to deformation. If you pull a material, does it stay the same or does it improve easily? Does it deform easily or does it deform gradually based at increasing stress? That is what this one is based on. And we discovered that we have improved stiffness over the commercially available material. The commercially available material is in blue color on the left-hand side. So clearly our material is a lot better than what is in the market. So this one is showing the effect of particle size that I showed you at the beginning and how much the strength improved, even with the addition of plasticizer. And there are work that are still going on. As I mentioned, this is a preliminary data, and we have some more recent data that are not presented here that are showing some clear improvements. Well, when you have improved strengths in engineering, most often it's at the expense of what we call percentage elongation or ductility of the material. When you have sudden increasing strength, you need to work on improving how much the material is able to deform before it breaks. So this is an ongoing work to improve the ductility of the material. We are getting close to where we expect to get to in the preliminary work. Then these are data for flexural stress, how much load the material can sustain before it breaks under lateral loading. Our materials demonstrated significant improvement over commercially available materials. Then for impact, we have scattered data that we are still observing and working on to ensure that we improve upon. Then for characterization analysis, it's usually good to look at what is inside the material, what is causing failure, where does the failure originate from and propagate from. So we look at the microstructure of the samples that we fabricated, and we were able to see that there were some agglomerations that occurred in the process of processing the material. And with the recent improvement or advance that we were able to record in getting proper sizing of our material, we hope that that will be resolved. So in conclusion, we can say that casein is showing us very promising results in terms of its usefulness for engineering applications. And this one is demonstrated based on the mechanical properties that we can see. And ultimately, our plan is to use casein exclusively without the commercially available material that are currently used in this study. Thank you. And we want to thank the Dairy Innovation Hub for enabling these studies.